Welcome to our new unit, Algebra 2 students. We are now in our sixth topic. It's chapter 4 in the textbook, so I'm just going to be calling it chapter 4 rather than topic 6, just to keep the numbers not mixed up. So in chapter 4 in the textbook, we're going to be looking at exponential functions. So we've been seeing a lot of functions this year, right? Chapter 1 was all about what a function is. We looked at quadratic functions and polynomials. We've taken a look at rational functions, and now we're going to look at exponential functions. And exponential functions are functions that you've probably thought about before. Big picture, maybe you haven't thought about it so much in the formal way. To connect it, we're going to be looking at an example with Alice in Wonderland. So feel free to read through the directions, and then there's a couple of questions here, so I'm going to just zoom in on these questions. So it's going to ask you to think about what happens to Alice if she eats 2 ounces of cake versus 5 ounces. We'll want to read through the rules that say, so there we go, that whenever she drinks something, she gets smaller. And whenever she eats cake, she gets bigger. And Carol doesn't really say how much bigger or smaller or even how tall Alice is to begin with. So we're going to just kind of make up some numbers. We're going to say maybe she starts at 5 feet tall. And let's say every time she eats cake, for every ounce of cake, her height doubles. And let's say that for every ounce of beverage, she has her height cut in half. So let's use those as our kind of assumptions going forward. So what I'd like you to do, I normally have this as an investigation where students work through these questions and then kind of check in with their groups. So since this is a video recording, I'm going to ask that you pause the video and kind of think through your answers and then unpause, and I'm going to discuss a little bit and you can kind of verify with me. So I'm first going to, real brief, talk through the height idea here with the cake. So notice I've got some information here for what happens to Alice with 2 ounces versus 5. Remember, she doubles her height every ounce of cake. So for each ounce, you're going to double. And then to get a general rule of her new height, it's always starting with her old height. Notice it's in blue. And then you have to multiply it by powers of amounts of 2, right? 2 raised to some power. And the power that it is, right, squared versus to the 5th, if you look back here and here, that was dependent on just how many ounces. So if we're kind of generalizing it to C ounces, it would be to the power of C. Okay, go ahead and try out the beverages as well. Okay, and then here is the thoughts for the drinking of the beverage. Remember, that will cut her height in half, so I'm doing it like times 1/2 rather than doing divide by 2. If she does 4 ounces, it's like multiplying by 1/2 4 times. You can also rewrite that as 1/2 to the 4th power. Same idea for the 6th power over there as well. So your general rule is original height of 5 times 1/2 raised to a power b, and the power is just how many times she is taking a drink, right? So you can really see that exponential functions deal with this kind of trend and structure here where you've got something raised to a power. And you might have a starting value, like we started with 5 and we were adjusting it. We're going to now kind of look a little bit more formally at what a function can look like. So here's an example that's kind of reminiscent of the Alice function, right? Like 5 times 2 to a power. That's like her growth function. So think about how this is different. This is our exponential function from something that we've seen before. I use the word power function, but you could also call that like a quadratic function, right? That looks like a quadratic function or parabola. Notice the difference in what these equations are looking like. Normally, we have x being raised to a power. In this case, we have a number raised to a power where x is the power. So in this case, we're kind of plugging in our power, right? Or our input is our power. Is another way to think about that. Input is your exponent, right? So it's just a little bit of a different placement from what you're used to historically in math. If you would like a general rule, this is kind of how I prefer to think about the general rule. we generally have a number in front. Remember, that was just like for Alice's height. I'll do the height example. We started with 5, and then we multiplied it, right, by 2, raised to some power. And that power we can call x if we like, right? So your starting value is in blue. So A is like your starting value. Oh, and I think I wrote that, so I already typed it, so I'm going to not rewrite it. A is the original value. And then B is your multiplier. So that's going to help you either grow, right, or shrink. And we'll look at a couple examples, and I'm sure you guys are kind of getting a sense of what kind of values would help us grow or shrink, even just from the Alice example, using the 2s and the 1/2. I think you could probably make a thoughtful hypothesis at this point. So we're going to look at a value to graph. Notice this one doesn't have a number in front of the 3. Like, this is kind of thinking of like, you could think about it like 1 times 3 to the power. We're starting with a value of 1. We don't always need to have a starting value like we did in the Alice problem. So we're going to practice graphing this. So the first step to doing a graph, and remember, feel free to pause at any moment if you need to go grab some graph paper, if you need to pause and draw something in your notebook. This graph will be pretty easy to put in a plain line sheet of paper if you need to. But the first step, and I think you guys got a little bit more comfortable with this in our rationals chapter, is just making a table, right? That's really the best way to get a sense of our inputs and outputs. So I'm going to just do -1, -2, 0, 1, and 2. Anytime I've got a function, those are kind of the go-to values that I'll plug in, just to kind of get a sense on each of the sides of my axes. So if I plug in, I'm going to plug in first 1. We're going to start there. So 1 would be 3 to the first power, or 3. So 1, 3. Plugging in a 2 would be 3 to the power of 2. Remember, the input is representing the power. 3 squared is 9. So 5, 6, 7, 8, 9. And what you'll notice is we generally don't go too far out because it grows pretty fast, right? If I plugged in 3, I would get 27, and that's going to be off my grid. So that's another reason why I really do like to stay a couple above 0 and a couple below, because otherwise you start getting off of your grid. If you do run into that, if you're asked to graph a function and you don't have any other ideas of clean things to plug in, what you could do is, like, put like 3, 27. You know what I mean? It's okay if it goes off if you need a 4th point or something like that. Like if you were asked to graph a specific number of points. But I just try and stick with these numbers personally. Plugging in 0, anything to the 0 is going to be 1. So that's actually going to be a point for a lot of our exponential functions. Except if you have something like, remember with the Alice problem, if we had like 5 times 3 to the x, this would be like we're tripling her height, just to kind of connect it to the Alice. In this case, we have a starting height of 1. For the Alice problem, if we had a 5 in front, we would, at the end, multiply by 5. So everything would, be increased in this case. But not to worry, we don't have anything else going on right now. 3 to the negative, I'm going to do 3 to the negative first power and then 3 to the negative second. So 3 to the negative first, remember that's 1 over 3 to the first. Anything that's negative exponent in the numerator, we move down. So it's just 1/3, so I kind of just eyeball it. If you do 3 to the negative 2, that's going to be 1 over 3 squared, or 1 over 9, which is even smaller, and that's when it gets really hard. So I generally will kind of stop there. That's like the smallest that I'll really go to. And then you're going to connect it. Arrow to show that it continues on either side. And then a question to think about, right? If I'm ending up in negative numbers, like if I do 3 to the negative 4th, 1 over 3 to the 4th, which is just like 1 over a larger number, right? I could do 1 over 3 to the 100th power. Think about the fact that because that's always 1 over something, we're not really ever going to get a 0, right? It's going to get kind of close to 0, but if you have like, for instance, I'll find what 3 to the 4th is real quick. Looks like it's 81. All right, that's going to be a small number. If you keep doing it times 3, you're going to get like 1 over 243. So keep in mind that it can't equal 0. So because of that, you might be kind of thinking about this. There's actually an asymptote just because it's not really feasible to get that to become a 0. So there's actually an asymptote at y equals 0 because when we do 3 to a power, we're never really going to be able to get it to become a 0. We can get like 1 over a number, we can get 1, and we can get other numbers like, 3, 9, and so on. So if I want to describe the end behavior, think about on the far left side and the far right side. So I'm going to do far left, far right. And I'm going to use a little bit of notation. You guys have seen a bit of this before. I'm going to say for far left, as x gets smaller, it goes towards negative infinity, is getting small. That's saying like going this direction. As the function goes that way, what's the graph doing? Y is getting close to 0. It's kind of hugging that asymptote. Whereas as I go to the far right, and so on the far right side, that's going to be as x goes towards positive infinity, as it's getting really, really big. And I'll kind of highlight this here. It's like going upwards, right? Focusing on what the function's doing that direction. It's just going to get bigger. So I'm just going to say it's approaching positive infinity. As my inputs are getting bigger, my outputs get bigger. Whereas remember on the far left, as my inputs were smaller, more negative, they got closer and closer to 0. Okay, so this is just practice notation. This kind of stuff you guys will definitely see more in pre-calc next year. So I want to get you guys comfortable with writing that notation. Okay guys, so for this next one, we're going to do a similar strategy where we're going to do a table. Right? If I do 1 first, right? 1/3 to the first power, that's just going to be a third. So I can plot that point. It's going to be like somewhere down there. If I continue, notice it's going to start getting more and more small, right? A 9th when I square that. So it's like continuing on. So we really want to try the 0 and the negatives to see if we get any better luck. So when I plug in 0, anything to the 0 power is going to be a 1. That's looking a lot nicer and more clean. And then this one's a teeny bit trickier to the negative first power, right? 1/3 to the negative first power. I'm going to attach exponents to both. Negatives on bottom, move to top. Negative exponents on bottom, move to top. Negative exponents on top, move to bottom. Remember, we're not moving negative numbers, it's just negative exponents. So just remind us that we're plugging in -1. It's going to turn into 3. So it does get bigger going backwards, which is a really interesting thing. And that kind of makes sense, right? As if it's shrinking going the other way, it would grow going backwards. Doing -2 would be a really similar process. 1/3 to the -2, you would apply the negative second power to both. And then negative exponents on the denominator, move to the top. And vice versa. That's going to turn into 9/1 or 9. You're probably seeing the pattern as well. So you can also use the pattern to kind of help you figure that out. Okay. It is really important to remember that exponent rule that we did talk about in previous chapters about how to move negative exponents around. That's going to be really useful. I'm going to connect my points. Right. Get the general curve. It's going to go up here. Notice it's trending towards 0. It's never quite going to get 0. Same thing as before, because I'm always going to have like a 1/3, a 9th, a 27th, right? Plugging in positive numbers is going to continue to be 1 over a number, and that can't really get you 0. It can get you close. So we're going to have the same asymptote. Draw that in. And then for our end behavior of this, I'm going to pause to write out the structure. Okay, so as x gets towards negative infinity, y is continuing to increase towards infinity. As x increases towards negative or positive infinity, y is getting really close to 0. It's hugging that asymptote. And then our general rule for which functions will give us growth, like the first one, compared to decay, like the second one, is what value B is. So take a look at the different options.